Hello everyone. Today we've got a couple of further pure past paper questions. I'm not actually sure which paper these are from because they were sent to me by a viewer. I'm going to ask that if you are that viewer, please can you drop in the comments which questions these papers were from, because that would be very appreciated. Alright, so the viewer wanted me to go over the topic of kinematics because they had some difficulty with it. And some good news I have for you is that kinematics as a topic, once you understand the basis of it, it's reasonably easy to just get really good at these questions with practice. Because once you know how to do them, they're very easy marks. They don't require much creativity once you've learned the content. So that's quite good. Or at least that's my assessment of it. Anyway, the basis of kinematic questions that I want to talk to you about is that they all focus, at least in IGCSE further pure maths, on the motion of, for instance, a particle along the x-axis. So this is positive x and negative x. So this particle moves along the x-axis. At the start, it might be at the origin or it might be at some other point. It never moves along the y-axis. And so the y-axis is irrelevant. So the three properties of the particle that kinematics questions will focus on is firstly its actual position at any given time, xt, and it doesn't necessarily have to be a function of time. You just know that the position of the particle x is this, represented by x, as it's an x coordinate as it's on the x-axis. And the next quantity that matters is the particle's velocity. And the velocity is expressible as the change in x per second at a given point in time. So Vt is also equal to dxt by dt. Or rather, it's the differential of x with respect to time, which you could also write as x prime. And the reason it's the differential of the position with respect to time is because, say you have the particle at a given point in time t, and after moving over a infinitely small change in the time, dt, given this change in time, the particle moves from this position A to this position B, where the original x position is at point A and the final x position is at point B. The change in x positions, while normally it might be called delta x, given the fact that this is an infinitely small time, can be called dx, because the d as a letter that is the lowercase form of capital D, which is basically this, because this Greek letter delta is what we usually use to symbolize change. There's the lowercase delta, which means a small but not infinitely small thing, and the Roman D, English alphabet D, which represents infinitesimal or infinitely small changes, allows us to represent this quantity, which is the infinitely small change in x, over an infinitely small change in time dt. So the velocity of a particle here, v, is equal to the amount it moves divided by the time it takes to move through that distance. And this d, instead of a delta, just represents that we're reducing the time we look at all the way down to 0, such that we can find its velocity at any one point in time or any one point on the x-axis. So the cool thing about this is that this is actually the origin of calculus. Calculus was not first conceived of as a way to extend maths that was originally not interesting enough. It had an actual practical purpose, which was to model the motion of the objects in the universe. And without that purpose, there would have been no need for it, or at least we know that it wouldn't have appeared so early. Because this application of calculus, thinking about how this change over a certain time can be reduced to zero, and that you can still get a sort of a value of a velocity for a particle that is completely still, given that you're not changing the time. This is basically why calculus was invented, for kinematics. So it's a little hard to explain conceptually that velocity is the change in position over time, but if you look at it on a larger scale, such as this particle moves 3 meters in 1 second, then you can see that the velocity is the delta x divided by delta t, which is 3 meters per second, right? But what calculus does is it takes this 1 second of measuring time and it reduces it mathematically all the way down to zero, because it allows us to express how the position of the particle, or rather how the value x is changing with respect to time, even without the data that we might usually have to collect about where the particle is at given points in time. You don't need 2 points of information to find the change in v with respect, or the change in x with respect to time, if you can use calculus. But if you couldn't use calculus, then you would need to know about this position A and position B and the time between these two locations, which would also be inaccurate if the particle had a changing velocity, which it often does. And that brings us to my next point, where we can think about acceleration as a physical quantity being the change in velocity, dv, over the change in time, dt. If a particle has a certain velocity v, and after an infinitely small amount of time it has, or let's call this v0, and after an infinitely small amount of time it has another velocity v1, and it takes dt to move between these points, well, the little change in velocity, which I'm going to draw as a differently colored arrow here, this little change in velocity is the acceleration that the particle has experienced. Or this little change in velocity, dv, over the time taken for this change to happen, is the acceleration. It is the rate of change of the particle's velocity with respect to time, which is expressed in units of velocity, which is meters per second, whereas velocity, being a change in position over a change in time, or rather a change in displacement from the origin, which is measured as the coordinate x, over a change in time, is in units of displacement per second, because it's a rate of change of displacement with respect to time, or meters per second being our units for velocity. So I admit that may not be the most clear explanation, but I hope at least that it serves to clear up why, when you have a function for a particle's position x with respect to time, you can differentiate it with respect to time to get dv by, or rather, to get v, which is equal to dx by dt, because differentiating allows you to go from x being some function of t immediately into this change in x divided by change in t, and how differentiating v might enable you to go immediately into the change in v divided by the change in t, which is acceleration. So if differentiation works to find the rate of change of something, how do we know the sum of all the changes that might happen? Well, just think about it for a moment. If you want to know how a particle is moving at a given time, then you'll want to sum up all the little changes in its position. So if x is its position and dx is a change in its position, then you'll want to sum all of the little dx's until you get that actual position, x. So like, if I had my particle at the position 0 when time was equal to 0, and then it moved to position 1 and position 2 and position 3 once per second, then we know there was a delta x of 1, a delta x of 1, and a delta x of 1 3 times. And by summing up these delta x's, and you'll notice I just drew an integral sign, which sort of gave away where this explanation was going. If you sum up all these delta x's, it takes you to the actual value of x. So what we're doing when we sum up dx is we're summing up these changes in x that are all so infinitely small. So how does this help us? Because we know that the integral of dx would be x, but how does this help us? Well, we know that velocity is the rate of change of distance with respect to time. And since dx is sort of a change in displacement, and dt is a change in the time it is, these are sort of physical quantities that we can mess around with. So if we want to multiply both sides by the change in time dt, then we get v dt is equal to dx, which means that the velocity multiplied by the time in which the velocity can act is equal to the change in position that the particle experiences. If there is a velocity of 3 meters per second as a property of the particle at a particular moment, and it is allowed to act for a certain amount of time dt, then this is going to multiply to equal the change in the displacement of the particle over that time dt. And so instead of summing all of the little dx's to get x, we can sum v dt. We can sum all of these. We can sum all the v dt's to get x, our displacement. Because each of these v dt's is one tiny change in our displacement, and summing all the tiny changes in our displacement gets us to our actual displacement. So mathematicians, as you might have realized where this explanation is going, mathematicians don't write the word sum every single time. I've drawn this S really big to get the point across that this summing of whatever is next to it with a calculus D involved is integration, because the integration symbol is similar to how S used to be written in English, and well, that was several hundred years ago. People don't do that anymore, but this has kept its meaning as a continuous sum of all the little pieces of something. So our equations that we have worked out up here, the fact that the sum of all the little bits of x dx is equal to x, and the sum of all the little bits of v dt, given that v dt is equal to dx, the velocity times the little change in time is equal to the little change in displacement. The sum of v dt must be equal to the whole displacement. this statement leads us to that the integral of v dt is equal to x, because it's really the sum of all the little pieces of dx, the sum of all the little changes in displacement. And this extends to our acceleration thing, because acceleration is the change in velocity over time. So you can see how multiplying both sides by the change in time, acceleration of a particle multiplied by the time in which that acceleration is allowed to take place gives us a change in velocity. So surely, if you sum up all the little changes in velocity, dv, that's going to be equal to summing up all the little changes in time multiplied by the acceleration that they experience at that time, or the integral of a with respect to time, or the integral of a times dt is equal to the integral of dv. So I hope that was a good explanation as to what kinematics questions actually do. Now I'm going to talk through these questions, but I won't go so in depth on the kinematics explanation, because you can always go back to earlier in the video if you are interested. I've just realized that I should move this and this to a new layer. So that I can keep it while I delete everything else. So this is moved to a new layer, and just skip to later in the video if you don't want to see this. Move this to a new layer. You go into our background layer and delete all. Okay, that was pretty smooth. Yeah, so if you're interested, if you're curious at all, I'm using Smooth Draw 4, which is one of the softwares that was used by Khan Academy when they make videos. So that's just for your information if you're curious. And let's keep moving with the question. So, a particle p is moving along the positive x-axis. At time t seconds, the acceleration of p is given by a is equal to 6 minus 4t. Now remember how the acceleration is the differential of velocity with respect to time, the change in velocity over time, which is equal to the change in displacement over time, aka d squared x divided by dt squared, or the second differential of x with respect to time. So those are just a bunch of different ways of thinking about the acceleration. And you can integrate to get from acceleration to velocity, and from velocity to displacement. So when t is 0, p is at rest, so this piece of information lets us know that, well, let's just write this out first. A is equal to 6 minus 4t. When t is 0, p is at rest. Okay, so when t is 0, that means the velocity of p is 0 because the particle is at rest, and the displacement of p from the origin is 5 meters. So when t is equal to 0, the displacement is 5 meters. Like it says, it doesn't always start from the origin. time t seconds, the velocity of p is v meters per second, and the displacement of p is s meters. Okay, so instead of using x, we're going to be using s for displacement, which is what physicists use when working with particle motion. So how might we find v? Well, first, we've already been through why it is the integral of acceleration with respect to time. So just integrating, we get the integral of 6 minus 4t dt, which is 6t minus 2t squared, using the power rule to go from 6 integrates to 6t and minus 4t integrates to minus 2t squared, plus c, because it's in an indefinite integral. So v is equal to 6t minus 2t squared plus c, and now we just need to find out what c is. So using the information that v is 0 when t is 0, so you write as v is 0 when t is equal to 0, 0 is equal to 6 times 0 minus 2 times 0 squared plus c, and all of these terms cancel out because they're multiplied by 0, and you get c is equal to 0. So this lends you to the information that the velocity is 6t minus 2t squared plus 0, which I'm not going to write down because we just know that this c, the constant of integration when doing an indefinite integral with no bounds, is equal to 0. So v is 6t minus 2t squared. Now, what next? Find an expression for s. Well, we've also been over why the displacement is equal to the integral of v with respect to time. So this is equal to the integral of 6t minus 2t squared dt with respect to time, which is using the power rule. So 6, well, the power here is 1, so 6, well, 1 plus 1 is 2. 6 divided by 2 is 3, and it goes to t squared. And then the next power up is 3, so 2 divided by 3 minus 2 over 3 t cubed plus c. And as s is equal to 5 when t is equal to 0, 0 is equal to 3 times 0 squared minus 2 over 3 0 cubed plus c, and these terms all are eliminated because they're multiplied by 0. And, sorry, this is not 0. 5 is equal to 3 times 0 minus 2 over 3 0 cubed plus c, and that means c, our constant of integration, is 5. And this constant of integration represents the initial conditions of the particle. So while you may want to write it out like this in an exam, you don't necessarily have to, as you could just write initial s is equal to the constant of integration, where the constant of integration is what you mean when you want to talk about this plus c at the end of an indefinite integral. So c is 5, that means s is equal to 3t squared minus 2 over 3 t cubed plus 5. So that's your expression for s. For t is 0, p comes to instantaneous rest at the point A. T is greater than 0, p comes to instantaneous rest at the point A. Alright, so for part B of this question, we know that t is A when p comes to rest, and p coming to rest means that its velocity is 0. For an instantaneous moment in time at this time A, its velocity is equal to 0. V is equal to 0. So since V is equal to 6t minus 2t squared, as V is 0 and t is A, are the pair of conditions we look for, 0 is equal to 6a minus 2a squared, or moving this to one side, 2a squared minus 6a is equal to 0. Just for my comfort, this is a personal preference as to how you do the quadratic equation. Factorize a out and divide all the terms by 2, so you get a squared minus 3a is equal to 0, then a minus 3 is equal to 0. and that means either a is 0 or a is equal to 3. And since a is greater than 0, as stipulated in the question, a must be equal to 3. So that's the time 3 seconds when the particle is at rest. But it also wants us to find the distance OA. Well, the distance OA, you've got to be very careful, is not the same as the displacement of the particle. Because, actually, no. In a physics sense, it is not the same as the displacement, because if you were a physicist, you would look at this problem and say displacement is from either the original position or some arbitrary other position. And your first instinct might be to think that it's a displacement from its starting point 5 meters away from the origin, when in reality we're looking at displacement from the origin. So our function s is actually perfectly valid when it comes to dealing with the displacement of this particle. So we want s where t is equal to 3. And rather, it's looking for a value of t, so just write this here as 3, or more importantly, you could write 3 seconds. Although I don't think seconds is necessary since this is a maths paper, not a physics paper. So we want the displacement when the time is 3 seconds from beginning, which would be equal to, given our expression that we found for the displacement, 3t squared minus 2 over 3t cubed plus 5, which is going to be 3 times 3 squared minus 2 over 3 times 3 cubed plus 5, or 27 minus, well, this is 27. 27 divided by 3 is 9. 2 times 9 is 18, plus 5, which is, well, 27 minus 18 is 9. 9 plus 5 is 14. 14 meters is the distance from the origin to where the particle's current position. So this is just sort of, you substitute the value of time that you got earlier in the problem into the displacement function. Okay, so this question is pretty much done. As always, ask me in the comments if you have any questions about it, and I will respond. Or alternatively, you can email me at watchmedomath@gmail.com if you have any questions about this problem, or you have a particular problem or topic that you'd like me to do in a video. So, now let's move on to another question. Just to make sure that our work doesn't get confused, I'm going to get rid of this particular thing, but we'll know that all the purple work is from the previous question, and I'm going to start writing in blue now. So, a small stone is thrown vertically upwards from point A above the ground, So it seems like we're dealing with the y-axis of displacement here. So you'd have a person standing on the ground, chucking a stone, where the stone leaves his hand at some point A. Let's make this the time axis, and let's make this the y-axis, or rather the height axis or displacement axis, where we're going to call displacement s, because that's what they use in the question here. The height of the stone above the ground is s meters. Until the stone hits the ground, s is equal to 1.4 plus 19.6 t minus 4.9 t squared. So write down the height of A above the ground. Well, when a question just says write down, it usually means that there is a very obvious solution. And in this case, there is, because it starts at a point A, and in doing this, you can sort of look at this quadratic and go, right, A is when t is equal to 0 because it's the starting position of the stone. If t is 0, this term must be 0, and this term must be 0 because they're multiplied by t. And so the only value in this equation that remains existing when t is equal to 0 is this 1.4 at the beginning. So as our answer to A, s is going to be equal to 1.4 meters upwards. Or rather, because it's s meters, we don't need to include the units. S is equal to 1.4. Find the speed with which the stone was thrown from A. Alright, so how might you do that? Well, we know that the speed, the velocity, is the differential of displacement with respect to time, ds by dt. If s is equal to 1.4 plus 19.4 t, I think it says, 19.6 t, minus 4.9 t squared, then we can differentiate this with respect to t using the power rule because this is a polynomial. 1.4 is a constant, so it's eliminated. 19.6 t is the linear term, so we take the coefficient, 19.6, then minus 4.9 t squared. Bring the 2 down, we get minus 9.8 t. And when t is equal to 0, s prime is equal to, or s prime, prime here meaning differential with respect to something. So s prime, we should rather write v because it's more appropriate to the question case. V is equal to 0 plus 19.6 minus 9.8 times 0 because t is 0. So velocity is 19.6 meters per second. So we want a speed, not a velocity v meters per second. The speed is the entire quantity, 19.6 meters per second. And instead of seconds to the power of -1, you can also write meters per second with the slash or fraction sign representing a per. And finally, C, find the acceleration of the stone until it hits the ground. Until it hits the ground. So, until it hits the ground is not a mathematically difficult thing to deal with, it's just a common sense notion of the stone will no longer fly once it hit the ground. Acceleration here is the differential of velocity with respect to time, or rather the rate of change of velocity with respect to time. And since velocity is 19.6 minus 9.8 t, we'll write d by dt, meaning differential with respect to time, or rate of change of this with respect to time. 19.6 minus 9.8 t, which is, well, 19.6 is a constant term, so it becomes 0, and minus 9.8 t becomes minus 9.8 because it's a linear term. And you can see that the entire system over any time will have an acceleration of 9.8 meters per second downwards, because our second differential of the displacement s is a constant and it doesn't change with time. So that's why it's a 1-mark question. The answer is a constant and it doesn't need to deal with change with respect to time. You may notice, if you have a good eye, that this is actually the value of the acceleration of free fall for gravity at the Earth's surface. If you were to jump, you would fall by accelerating at this rate. And I find that quite nice that they've used this in this kinematics question, because it's a real life application. If you stood in a field with a rock, throwing it from a point where you released it, where your arm was 1.4 meters above the ground, with a velocity of 90.6 meters per second, then your stone in real life would follow the same trajectory, or it would follow the same pattern of displacement from the ground level in terms of how vertical it was with respect to time, as in this question. So it's a very real situation. The acceleration of the stone until it hits the ground is 9.8 meters per second squared downwards. And on that note, downwards upwards is usually represented by positive or negative signs, given that we're just looking at acceleration in one dimension. So we might say 90.6 meters per second upwards being our initial velocity of the stone. And finally, D, find the greatest height of the stone above the ground. Well, ultimately, if it's a quadratic graph with a negative squared coefficient, minus 9.8, then a negative squared coefficient, or negative a, as you might know from the form of the quadratic equation at squared plus bt plus c. Since we have a negative a of 9.8, or rather minus 4.9, we know that there's going to be some kind of maximum here, if this is t and this is s. So the particle moves along. It doesn't move along this path because this is time. This doesn't represent any horizontal position. This is just the height of the particle with respect to time. And there is a maximum height at the bend of this quadratic graph. So how might you find the height of the maximum of a quadratic graph? Well, there's a couple of ways you can go about this. One way is by differentiating and then finding the point where velocity is 0 and putting the time element of this back into the question. And another one is by completing the square and using information from the completed square form of your function to get the maximum point. So, whoops. One thing that what we're going to do here is through the kinematics way, by finding the time at which velocity is equal to 0, because this rate of change, this gradient of s would be 0, as it's a horizontal tangent line. And then we're going to use that value of time t, or t0, to get a maximum height. So knowing that v is equal to 19.8 minus 9.8t, or 19.6 minus 9.8t, when v is equal to 0, 0 is 19.6 minus 9.8t, and we can solve the equation for t, so add 9.8t to both sides, you get 9.8t is 19.6, and divide both sides by 9.8. Using a calculator, this will lead you to t is equal to 2, or 2 seconds since you threw the stone. So since t is 2, we want to find the height of the stone when t is equal to 2, so we want s when t is equal to 2, or 1.4 plus 19.62 squared minus 4.9, minus 19.62 minus 4.92 squared. And if you were to put this into your calculator, you would get an answer for this, which is the answer for the whole question. Or we can use some clever mathematical trickery here, saying that this is, since this is 4 times 4.9 times 2, and this is 4.9 times 2 times 2, it'll be 1.4 plus, this is 8 times 4.9 minus 4 times 4.9, which will be 4 times 4.9. This is not a kinematics comment, this is just a comment on the calculation to make it easier for you. Plus 4 times 4.9, or as we know, this is already 19.6 plus 1.4, which leads us to a maximum height of 21 meters, which is the same as if you use the calculator for this calculation. The displacement when time is equal to 2 seconds from the start. So does it ask us for s of displacement? Nope, we just need to find the greatest height of the stone above the ground. So it's a height, not a value of s that's already in meters. So we're just going to write 21 meters above the ground. Lovely. Alright, so I hope that these questions helped you in your quest to understand more about the kinematics topic and further pure maths. I'm going to consider this a hybrid video of both an actual tutorial of kinematics as well as some example questions. If you are that student who requested this video, I'm going to be emailing you back to see how you found it and also to request the past papers you got this from. And finally, thank you for watching. If it helped you, please do subscribe, as there are new videos every Tuesday, Thursday, and Sunday at 6 p.m. Hong Kong time or 10 p.m. Universal Coordinated Time.